Good morning, ladies and gentlemen. My name's Gary Blackshaw. I work for Furse in Nottingham. I'm afraid my first and only language is English, so please bear with me. I represent a company called Furse. We're a very old company, 125 years old nowadays, and we've got a long past. Lightning protection has been going for 250 years when Mr. Faraday first came up with the concept. So we've been going 125 years. It first started out as a steeplejack company, and then over the years we got more involved with the technical aspects and the supply of materials into that industry. The place where we're based at nowadays was built in 1950. In recent years we've been bought and purchased by the bigger companies. So first of all, in 1998 we was acquired by Thomas & Betts, and more recently in 2012 we became part of the ABB family. Just to show where we are in the ABB family, connectivity and grounding, we support the local sales organisation. So as I'm sure most of you are aware, ABB are a very big company, 140,000 employees over the globe. And I just represent this connectivity and grounding. So we get involved with lightning protection, earthing, material supply and the technical aspects. We can help with design and specification. We're involved in all markets where we've had major successes. These industry segments are going to be familiar to yourself. These are oil, gas, petrochem, utilities, energies. This is the wind farms, this is the solar farms, this is the power stations. This is nuclear power stations. Rail infrastructure. This can be stray current earthing. It can be lightning protection for the stations. So we're involved in all aspects. My main topic today is general earthing. Earthing is not only for lightning protection, it's also power earthing as well. And there are differences between these. So when we're looking at earthing for lightning protection systems, I'm going to talk, I know there's several lightning protection systems. I'm going to talk generally about the IEC 62305. This is the one that we've adopted in England and is recognised all over the globe, and it's more of an active. Power earthing systems, this is applicable to everything that supplies power. Your substations, your power stations, your transformers, again, solar farms, data centres. The difference is with lightning protection, the lightning strike is very, very quick. It's 10, 20 microseconds. So the system is designed to accommodate such a short frequency. A high temperature is not really applicable because it's a fast strike, and the idea of the system is just to take that to Earth as quickly as possible. Remember, when we talk about Earth, we're always looking at the least resistance to Earth, the quickest path to Earth. So it's all about bonding, about allowing the current to flow equally. The power earthing, these are typically far lower values, ohms, resistance-wise, because we're looking at longer durations, we're looking at bigger currents. So when you get these power earthing systems, it's generally calculated to the specific requirements. This could be a utility giving you the maximum fault current, the time duration, and then the several considerations taken into account. So when we're looking at lightning protection, it's, as I said, to safely take the current to Earth. And the materials used is designed to effectively dissipate that lightning strike and withstand the stresses put on the lightning strike itself. Equipotential bonding is a critical part of lightning protection. This means that we don't want any flashover currents, so if we're talking air conditioning units, ladders and aerials, there's several factors that need to be bonded in to make sure that that earth goes, the electric current goes the least path to Earth. So the basic principles of lightning protection, I'm sure most of you are aware, it's to capture and intercept the lightning strike at the air termination network. Safely conduct the lightning strike to Earth, and then it's to dissipate it into the earthing system. And then, like I said, it's to provide the equipotential bonding. There's also the requirement to protect against the secondary effects of lightning protection, which my colleague from ABB will be talking about shortly. On an earth termination system for lightning protection, the earthing requirement is 10 ohms or less per earth. The standard recommends a single integrated earth termination system for a structure combining the lightning protection power systems and telecommunication systems. The main principles behind such a system is to ensure that the system's at the same electrical potential, so you've got that ease of current going to earth. With lightning protection, there's two general earthing arrangements. As you can see, you've got the Type A arrangement, which is the most common. So you've got the Faraday cage system, and that'll take the lightning strike to earth at several points. You've also got the Type B arrangement. In the standards that were introduced 1st of September 2006, now the IEC standards, it does try and push a Type B arrangement. This will allow the use of using reinforcement bars in the structure. Maybe an air termination network might be connected to a ring earth conductor at the bottom. So we can use the foundations as part of that earthing system. When we're looking at power earthing system, this is far more complex. This is, the earth is the mass of earth that we're talking about over a specific land. And we all know what the earth is. So it's a massive volume of soil and rock, and very large in comparison to the electrical system being considered. So the functions of an earthing system is to provide the path to earth through a system neutral. It's to provide that low impedance, the least resistance to earth, and it's to limit, as far as practical, the rise of potential. I will mention that a little bit later, but the potential is the dangerous effects of the electric currents that can kill. It's to eliminate persistent arcing. This is again dangerous, can cause fires and again cause damage. And it's to ensure that a fault which develops between high and low voltage windings can be detected by the protection system. There are several standards when it comes to earthing. Now, these are the BS standards I'm referencing here. These standards are recognised all over the globe. They're used in many countries around the world, and they've been adopted in certain aspects by the IEC. So it could be for electrical installations, substations, general power installations, and then you've got whether it's a power installation over 1 kV. I know there we've only got the one reference to IEC, but all these are used all over the world. Other standards that are recognised globally are the American standards. Again, it's substation earthing, and it's a guide for measuring the ground impedance, because we're looking at major power systems with lots of power. So we've got to make sure that the standards we're working to are correct. And it's also critical to appreciate the standards that we're working to require different figures, different elements to put into the calculations. So it's critical to know what earthing standards we're working to from the start. Now, I've mentioned the BS and I've mentioned the American standards, but there are many other standards, obviously, around Europe and different areas of the globe. As an organisation, we have to try and work with all the relevant standards to make sure we can give that technical support to our sales colleagues. Soil resistivity. This is a topic that is critical for an earthing system on both lightning protection and power station power earthing. It's very important to get the correct readings. The resistance to earth electrode is the resistance per ohmmeter of a metre squared of earth. So the resistivity of soil can vary geographically on site and dramatically at different depths. Nottingham, where I'm from, we have sandstone 1.5 metres below the ground. I know in this region you've got a lot of sand. So there's different levels, have got different resistance. And then there's resistance measure techniques that can formulate the depth of the resistance and the different layers. From that, this can be used in the calculations to help give the correct earthing system to make sure that it's safe. When it comes to soil resistivity, you can do the soil resistance testing, but like I say, the types of soil. The moisture content, obviously if it's wet, it's a better conductor. This has to be taken into consideration when designing an earthing system. The temperature depends on the time of year. Certain regions, like this region, you can have highs of 30, minus 30, so these have all got to be considered when doing the earth resistance. The compactness and density, if it's compacted and it's tight, it's going to be a better conductor. If you've got a lot of air gaps, it's not going to be as good a conductor. All these are considered. When we're measuring the soil resistivity, like I say, we measure it at the different depths. This is normally done by a Venner system. I don't know if anybody's aware of this, where the probes are put, 4 probes are put in at periodic places, 10 meters apart, 5 meters apart, 2 meters apart. This can provide an accurate definition of the resistance at that level and at the depth required. So if you've got 10 meter spacings, you're effectively measuring 10 meters down. When it comes to power earthing, the materials tend to be totally different to lightning protection. As we can see here, this is a typical earthing grid. The idea is if anybody steps on that, the potential's negative, it's fine, there's no big potential, it's not going to kill anybody. We do the exothermic welding process. This is welding copper to copper. This is what we normally use in an earthing system to our standards. And this is a high temperature, 1,000 degrees. It creates a portable earthing solution. It's a permanent joint. Earth electrodes, I'm sure most are familiar with. And the actual conductors, like I say, we opt for copper. I'll explain a little bit later why we go for copper rather than the likes of galvanized steel or stainless steel. When we're looking at earth electrode, like I say, the copper, it's a better conductor of electricity. It's easy to use. And as you can appreciate, copper's been in the ground for thousands of years. It tends to last in the ground for many, many years. There's no issues with degradation of the materials. This is normally put together through an earth grid or a ring earth arrangement. The earth conductor must be capable of carrying the maximum expected earth fault current and leakage current. This is determined at earthing design, and when we do the earthing design, like I say, we look at the standards we're working to and we take effects like the soil resistivity into place. This can give us what we need to do current carrying capacity wise. When it comes to earth electrodes, these are often used with the conductor, with the ring conductors. The copper bond rods are the rods generally used all over the globe. It's molecular bonded copper, so you've got no issues with galvanic corrosion between the steel and the copper. It's very strong and it's got high resistance to corrosion. High steel strength, tensile strength means that you can drive these at deep depths. So when you get an earthing system, globally it's the copper bond rods normally used. If you've got instances where you could have a corrosive soil, you may require better earth readings. Certain regions, particularly the Middle East, often opt for solid copper rods. The problem being they're then very expensive, but they are very good and they'll last a long time. So they're used in applications where you will get a better reading, but then the commercial aspect will come into play. We also do a stainless steel rod. If you've got high pH systems and even copper can be corroded, then they might opt for a stainless steel rod. Again, certain regions and certain applications will ask for these stainless rods. So we as a company and organisation recommend copper bond, solid copper or stainless. One of the problems, and I know this region is a big user of galvanized steel on both the earth rods and the copper, the conductor. So if you're using galvanized steel, copper is resistant to corrosion in most soils. The zinc coating on the galvanized steel is sacrificial in most soils. And basically what's going to happen, as the zinc corrodes, it will then start corroding into the steel. So the copper and the copper bonded will last far longer. Here's a typical example of a copper bonded rod and a galvanized steel rod. This is 12 years in the ground, and you can see that that's heavily corroded. Once it starts corroding, it's not going to be effective. So the reason we recommend copper bonded is the general lifespan. It's the efficiency of the system. This example, you can see here, that's corroded away. So as an earthing system using galvanized steel in this instance, this is 11 years. That would be ineffective. It wouldn't give the safe passage of current to earth. It would fail. So this is a loss of zinc basically resulted in catastrophic failure. Here's a graph we make reference to. So if we're looking at the life expectancy, galvanized rod is 15 to 20 years. I know those examples are a lot less. And then it shows you the copper bond, different copper thicknesses and the stainless steel by far outweigh the lifespan. So when we're doing a comparative cost, you can see that the zinc galvanized isn't effectively cheaper, isn't commercially benefit because you've got a cheaper option with a copper bond. I appreciate this region does use a lot of galvanized, but you've got to bear in mind this is not just the earth rods, this is the conductor as well. So like I say, there's different elements that can affect the corrosion and the chemical nature of the soil, the acidity, alkalinity of the soil, any salt content present, and again, presence of bacteria. This can be an issue with the lifespan corrosion of these materials. When we're looking at earthing, I'll explain a little bit later, but this is the area that causes the problem. It's when you've got a difference. So if you've got an operator, a machinery, and that becomes live due to a fault, it's this difference that causes the issues. There's often solutions, a grid of copper, or in this instance, we've used a copper mat. So you'll see these and different sorts of materials. So when you're doing your earthing system, it's all about safety and saving lives. The different joints. In the UK, for instance, and the Middle East, the exothermic welded joint is specified by the majority of utility companies because it basically lasts, it doesn't corrode, it's got better current carrying expectations. The mechanical connections can fail over a period of time. Once you get moisture in those joints, they can fail in an earthing application. And then we've got the compression joints. The tools do bring those together, and you've not got rid of the ingress of water, but it's just showing some of the different connection types for all the earthing systems. This is my history. I used to be a welder, so this system here, the exothermic welding, like I say, it reaches 1,000 degrees. It's portable. It can create a joint in literally a couple of seconds. This is used on wind farms, solar farms, power plants. I personally have been involved with the training of many, many operatives on this system. It's a health and safety system, so it's something that we have to bear in mind. When looking at your earthing conditions, I've mentioned the soil resistivity can be an issue. We get involved with backfill materials. You might have come across carbon components like marconite. So typical application, you could have a borehole. So if you've got sand or you've got rock and you're going to struggle to get the right earth reading, we can put a borehole in place. We can dig a trench and we can put this earth conditioning agent in place. There's bentonite. What bentonite is, it's a moisture retaining clay. It swells up 13 times, 13 times its dry volume. It absorbs moisture from the soil, it keeps it wet, and it allows good conductivity. So when you're looking at that path to earth, this helps. Another area we've got, similar to the marconite product, is a Furse cam. This is a solution. So if you're looking at a solution where you need to improve the earthing, this is a mixture with cement, and it gives a permanent solution. If you've got an area like the Middle East, then you've got dry, it's not going to absorb the water, it could crumble. This is permanent. It's basically conductive cement. But when you're looking at applications for earthing and assistance, this is just one of these areas that can help. Briefly on step and touch potential, it's when the human body is accidentally introduced into that fault current. The current flow is dependent on many factors. This can be the footwear the guys are wearing, this could be chippings, rocks around a site. Most earthing standards set tolerable limits to work to. And again, it's all about the loss of human life. It's regarding the standards that you're working to. Just quickly again, I mentioned the step potential. It's that variance in between. If you put an earthing system, there's no variance. There's no equipotential difference. This is what kills people. There are standards for livestock, for instance, if it's horses or cattle, because you can imagine if you've got that voltage going across the front legs, it would go through the heart. It would kill them. So it's very critical to bear that in mind. The other one is the touch potential, because it's just going to transfer across. It's not just a step potential. We get involved with earthing design as an organisation, and like we're part of ABB now, it's a service we can offer. I've mentioned it's an accurate measurement of the soil resistivity. Touched on areas of soil resistivity, that's important for earthing design. If you've got a system that needs to be safe working conditions, then this needs to be critical. We need that soil resistivity data accurately, then we can put that into software that will give us the modelling. We can work out the rise of earth potential, and we can also ensure hot and cold sites to make sure that it's safe to work. A typical earthing design could be an array of conductor and earth rods. That's been determined by the soil resistivity, the fault currents, and other factors taken into consideration. Like I say, seed eggs, that's a worldwide it's a worldwide application that's recognised for earthing design, and we get involved with validation of existing designs and step and potential calculations. I notice my time is about running out, so I'll cut it there because I start going on to some of the materials for lightning protection. If anybody's interested in additional information, please see myself or my colleagues at ABB. I welcome any questions on this subject. I appreciate it's a quick snapshot of earthing. It's a very complicated system, it's a very complicated topic, but this is just a bit of an overview to give you an idea what's involved. Any questions? I believe I've got a translator.
Sorry, one question. Thank you for your presentation. My question is, what is your opinion, and do you use lightning receiver like early stream emission receivers, so-called active lightning protection system, according to French or Spanish standards?
Yeah, well,
we have quite low understanding here in Latvia. Could you explain something about this?
Okay. When it comes to active and non-active lightning conductor systems, the British standard based on the IEC is a Faraday cage system. The idea was all the standards were harmonised 12 years ago. The French and the Spanish didn't like the idea of harmonising the standards, so they've got the IEC recognition and they've also got their own standard. ABB as an organisation push and promote both systems. It's dependent on the local authorities. There are places in the world different regions that have banned, outlawed the ESC devices, but there are other regions that favour those. So it's a difficult question to ask. I can get you information by my colleagues on the differences. So as ABB, there's a company in France called Helita we work closely with, part of the ABB group, and then my company Furse, we're part of the ABB group. So the two systems are out there, and it depends on the region, if I was to be honest. But I can get information by my colleagues. It's a different subject, and it would be another 20 minutes, half an hour.
I understand that. That is quite legislation problem, but I interested your opinion about technical problem.
My opinion, I've got to be careful on this one, is the calculations for the ESE system are based on worst case scenarios. So a lot of it is theory rather than proven techniques, where the Faraday systems technique is a proven technique. So I would favour the Faraday cage system, but then for 25 years I've been working for Furse, so I'm going to be trying neutral on that one. Anybody else?
Thank you, Gary, about the information. My question is, as I understood from your speech, there are two different systems, one for lighting, one for earthing.
Yes.
It's always, or there is possibility combine them all together and then use, for example, for private houses, or they are separate, absolutely separate?
They are encouraged, providing the difference isn't too high, to be bonded together.
Right.
But they are two different systems.
All right.
So a lightning protection system, like I said, is for a short duration of that electric current, and then a power earthing is a different subject altogether. But they should be bonded just to make sure the equipotential is together.
Yep, thank you.